Okay, so the previous part was all about showing how those early two entries that have the microcodes are loaded. And speaking of the kernel, assuming that they are like in the right place, and the right place means that they would already be extracted and loaded by the kernel when an initramfs is provided, or an initrd. So what I'm going to cover in this one is how these folders were actually created by covering unmkinitramfs. And then I will make a preparation to what I already showed in the previous video, that is how the main, which actually has the real init, which would be the init that the kernel runs as PID1 in user space, how it is populated and why it is and how it is. So in the last lecture, the last thing we did was unmkinitramfs to the initRD, and let's just do it again to show that we're not cheating. So I'll do this, and then I'll run unmkinitramfs to boot initRD.image and to foobar. And we also did it with the v parameter, which showed us like, hey, the microcode first and then the rest of them. Okay, and initRD image would be a link to whatever I'm running right now, right? The initRD. Okay. So first of all, what does unmkinitramfs do? So we can of course go ahead and do man mkinitramfs and man unmkinitramfs, but I will not do that. I'll just show you. So there is a little trick in here. Why? Because if we go ahead and look what is the type of this file, let's make temp blah, and I'll change directory to it. If I look at this file, it will tell me it's a cpio archive. Let's see how big it is. 66 megabyte, which means if we don't really need some things in it, it can be a place for optimization. But it's a cpio archive. We know that it's a cpio archive. If we go and do, let's say, xdump to this file, just paste the path. Let's do -c. And see, we can see that it is a cpio archive because we have a magic code here, okay? 0707. Just write a quick note of what I'm saying now. We can see it's a cpio archive, not an extracted, or not a compressed archive, okay? So this will get important a little bit later. And because we know it's a cpio archive, then it's not like a compressed, then we can see in clear text also the path, okay? We have like the index, so we can see here like a kernel x86, kernel x86 microcode. These are like the folders, okay? This is the format of like a cpio archive. Is super trivial. So we can go ahead, look what's there, and that will be like, of course, the binary itself, okay? We can search for the next archive over there. I can just do space until I see something that perhaps will make sense, or I can just search for that for like the kernel, but I will not do that because it will be like wasting off our time. So we have a cpio archive, we're not lying. So great, let's go ahead and extract it. So if I go ahead and here do cpio-idv to this nice fellow, all I get is 3 files. And if I look at this, then I get only one of them, and the authenticamd bin. Actually, in this particular computer, I actually have an x86, an Intel processor, so it wouldn't even serve me, all right? So, like this one is like an Intel one. So it's not good, okay? So what's going on? How did you get to, how does the unmkinitramfs work? How did you get the RAM disk? So let's, in order to see that, let's go to our great foobar folder just to convince ourselves that here we have all of what we expect. Okay, and let's look at the file, which unmkinitramfs. Let's see what it does. So we start with the end. We have here split initramfs that receives the first parameter, that is the path to the initramfs. We have where to extract, and we have cpio opts that would basically be either show the verbose or do not show verbose. Here we have parse args or use a jar, not really interesting. Here we have some options for the extractions, no upload file names, preserve modification time, and so on. Great. And there we have a couple of functions that are like the core logic. So the main function would be split initramfs, okay? And it uses some utility functions. The utility functions that it uses would be to check if a byte is 0, does all kind of DD shenanigans. Read X, that will get an offset in the file, and it will use DD to skip a couple of this is the offset essentially. The first one will be the file, the offset will be the second one, and count will be how many bytes, this is byte size 1, to skip. So readx is actually going to tell me, hey, go ahead and give me, let's say, 6 bytes. Why do I say 6 bytes? Because it does look for 6 bytes over there, okay? And then it is going to do some graphing. And the other one, the last one, would be xcpio, which does the following. It's going to use, check out the T, it's going to use a couple of compression, or more precisely the compression methods, and it's going to test them to see if whatever this function receives is indeed an archive compressed with this algorithm. So it's going to test with gzip, zstd, xz, lz, lzop, and so on and so forth, okay? It will extract them, decompress them, okay? Here we can see gzip -d to the console, and it will pipe the result to cpio, okay? So this is a helping function that can help us to decompress a cpio archive if it is compressed with an algorithm. Great, so we can go back to the utility function. We can see that it has a while true here, another while true here, which means that we will break upon some condition. And let's see how we start here. We have the initramfs, we have a directory. We start with offset 0, and in the first offset we have end equals the value of start. Why do we use it? Because we're going to go over the entire file, the initramfs file, give it an offset, count where something ends, and at the end of it we're going to pass it via dd, make a stream out of it, and then do something with it, which possibly can be extracting a cpio. So let's have a look at what the function does. So here we go ahead, first loop, go ahead and skip some padding. Great. We're going to check a magic number and compare it either to, as we saw at the very beginning where I did the x-c, as 070701 or 2070702. And if so, we're going to break. Okay, that's how we do it, and we'll have like and if not, we're going to go ahead and read an entry from the file. So we actually read the entries, okay, and what the entries that we are interested in would be like the name and the size, and then we're going to go and calculate and skip, okay. We're going to skip like the offsets so that we can go ahead and go to wherever this binary data or not so binary data, we already saw in the eye that it's CPI archive, where the end of it is, okay? So essentially, what we're going to do is that if there is padding or if there is like nothing, then we're going to break out of this loop. Assuming it's not nothing, and it will be nothing, for example, if we do not have the magic number here, okay? This will be like the break of the first loop. Assuming that we have something here, look what's going to happen. We start with count equals 0, I suppose. Yeah, there it is. And then we're going to have it increased. So it's going to be 1 or 2 or so on. If it's 1, then we're going to call a directory early. Otherwise, early plus the counter. This is why we have early and early 2. Okay? What we're going to do with this directory, okay, is we're going to make such a directory. For example, make directory early or make directory early 2. Change directory into it. And over there, look what we do. We have a DD here that gets a start offset from the loop, a size that is the end minus start, we counted the end here, and we are going to pipe it into cpio and this nice fellow here, okay? So since we saw that we have cpio, this just extract them as is. So we can assume from here that we got like the early and the early 2 code. We can assume that early, which has the AMD code here, microcode, is the first cpio archive in this file, and right after it, perhaps after padding, there is early 2, which is the Intel one. Excellent. So where does the main come from? That's the next part. So the next part here would be, after we're done with that, if we actually add something like in the file, we're going to extract to the main directory. Now there is like an if-else clause here, and the reason for that is that what if I didn't have like this early or early 2? What if I don't have microcode at all? Can I still use the tool to extract my initramfs? The answer is yes, and this is this else. It calls cpio, that expect to see something compressed, the method that we saw before, on the initramfs and extract it. Okay, that's how it does it. Otherwise, if we have the scenarios that we have, so what happens is that it's going to go ahead and try to see if there is like it's not really important. It's going to try to create a temporary directory for the extraction right here. Okay, and what it's going to do here is going to do a cpio. xcpio, this will be like the temporary directory to extract to, and it will be it will call the utility function for the file, the temporary file that we are going to create here. Check it out. This is the DD thing. It's going to start from the end of like the early and early 2, and it's going to output its data into this temporary file. We could, if we wanted to, we could just skip that and pipe that, but in this case they did not write it like this. So this actually goes and call this xcpio, and that's it. Now this is how it's done, okay? And there should be a make dir main somewhere that I probably missed. So let's have a look at that. Yeah, so it says here that like it's going to extract into main. Let's see the parameters of xcpio. So xcpio receives a file that it wants to archive, and it has a directory that would be like the directory of the original last output that we had, like foobar in our example, and then /main. This is what was written there, and it's going to extract the archive. Okay, so excellent. So this is what's happening, and this is how it is created here. Now, what is created? So if we go to main, we can see that it is not so slim. It's 215 megabytes. And we already know that it has an init, and I will cover it. I think I already covered it in the past, but if not, I will cover it maybe in the next video so that we don't overuse it, okay? But bottom line is that there is an init here that is busybox, okay? And it creates some directories, it does all kinds of things, and at the end of the day, it runs a switch root here. Now, I'm not going to cover this right now, but I want to show you why we have 215 megabytes. So we have 250 megabytes mostly because everything in under user, okay? And if we get more specific, we can see that under user lib, there are 211 megabytes, okay? The other thing would be other user bin, okay, 2.4, and perhaps under sbin and so on and so forth. But we can see that most of the file here, as I mentioned in the previous video, are the same file. So they will have like a count of 99, okay? Because they will be hard linked to BusyBox. I put it in the reverse order so you cannot see it, okay? And the other one, some have like only one count, for example, for power off, for resume, for halt, for udev admin, which will be a link under system. If we go to lib systemd, what we will see is that we have systemd udevd for like enumeration of devices. If you use like BusyBox, you could use like mdef, for example. We can see that it is a link to bin udev admin, okay? So this is what we have, speaking of files. Now, if we go to modules, we have here the kernel that is related to this initrd, okay? And here we have like 144 megabytes. Let's have a look at like the structure. So we have all kind of crypto accelerator module. We have drivers for ACPI and ATA. We have clock drivers. We have firewire, GPIO, HID, I2C, input, network drivers, you name it. And obviously, when you have like a distro or like when you have a computer, you don't need almost any of these things. So if you want to save some size, the 66 megabytes that are compressed of the initramfs, or just 144 megabytes, you need to know what your system you have, and you can easily save more than 100 megabytes without any effort. The other side there would be this guy. So this guy would not be as big as you expect, okay? It will be around 12 megabytes. And the reason for that would be mostly using some standard C libraries, okay? So we have like a loader, and if we look like at libc here, we can see that size-wise it would be the same as like this is like on my host lib x8684 and lib c.so.6. So both would be like the same, okay, size, and and there are a couple of other libraries as well, and they take what they take. But so the takeaway from this is the zeros are of course links, but the takeaways for this is that it uses GNU libc on the RAM disk. If you don't need this, you can use muscle, you can use micro-C libc and so on. Great. Another thing that where you can save like a significant space would be the firmware. So if we look at this, we see that it's 55 megabytes. And there again, you would have all kind of things that you probably don't need. If you don't have like an RTL NIC, why have the firmware for that? If you don't have like a Mellanox or like Intel, why do that? Why use that? So the idea or the bottom line is to not use that if you don't need it. If you really need it, like for your computer, because maybe you want to have like network access for some common chipsets, then it's up to you to see what you want in and what you don't want in. And the other thing that we have here would be a minimal libc, a klibc, okay? So this is the description of what is extracted and how it is extracted and how unmkinitramfs or unmkinitramfs works. I don't know if I will do the next one again, but perhaps I will. And if I do, Then the next one will actually be what init does. I just covered a little bit of it, and what I said is important. It's a little bit pointless to go over like all the parameters, because you need, like there's like the debug switches and where to stop and what modules like to blacklist and yada 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 yada. And this is not entirely self-contained, meaning that I'm not only talking about running all kind of scripts, but I'm also talking about that sometimes there is like an executable that is running it that is a separate project. So I've told you that it does a switch root because it does a switch root, but we can go ahead and explore how it looks like, and this will not be done in this video. But as I said in the previous one, what I'm saying is just like it is. So if you watched it, then you probably trust me. And if you know me and if you liked what you saw, then you're going to go ahead and prove things to yourself, or to prevent, spending another 2 hours with me deep diving on really good things that other people did. But, that I don't know if people will see this video, so why should I produce it? All right, so great, awesome. So have a good one.